Good morning, JS students. كيفكم? Okay, so in this video we will revise شو أخذنا in numerical sequences. We started by learning about mathematical induction, which is one of the ways to prove a statement. Okay, other proofs need deduction and contradiction, but induction is usually used when to establish that a given statement is true for all natural numbers. Okay, so if a statement includes natural numbers, it's most likely to be used in sequences, يعني, the mathematical induction. We symbolized it by trying to climb a stair, okay? And now we have to prove three things in order to prove a statement. And we can just step on the first step on these stairs, okay? And if we were on whatever step, we can just climb for the step above it. Okay, by proving these two facts, and then we proved all the statement. We summarized it also in the letters TAPE. Okay, T is test. A, assume. We assume that we are on the nth step, and we prove that we can climb for the step above it. And then E, which is explain, okay, or conclude the result that it is true. Okay, for example, let's take an example. We want to prove that Pn, okay, Pn, which is equal to n into n plus 1 into n plus 2. We want to prove that this is divisible by 6. Okay, these are three consecutive integers. We can test it. Okay, the first step is test. For example, we can try P0. Okay, P0 is equal to 0 into 0 plus 1 into 0 plus 2, which is of course 0, and it is divisible by 6. Okay, so it is true. The first step is true. We can try to, this is divisible by 6. Okay, 0. So P0 is divisible by 6. Okay, we can try it for P1. We get 1 into 1 plus 1, which is 2, into 1 plus 2, which is 3. 2 times 3 is 6. Also 6 is divisible by 6, but there's no need. Okay, just finding it for P0 is enough. Okay, so in the next step we have to assume or suppose. So we say that suppose that pk, for example, pk is divisible by 6, and we have to prove what? We have to prove that pk plus 1 is divisible also by 6. Okay, so we know that pk is divisible by 6. Pk is simply k into k plus 1 into k plus 2. We want to prove that pk plus 1 is divisible by 6. Okay, we want to see if this statement is true or not. Okay, so let's start. We know that pk plus 1 is equal to k plus 1. So instead of n, we are putting k plus 1. Instead of this n, we will put k plus 1. And this plus 1, it will be k plus 2. The same goes for the third one, k plus 1 plus 2. So k plus 3. Okay, we can expand this and write it as the k plus 3. Check what we will do here. We will write it, we will expand k into these two factors and then 3 also into these two factors. Okay, so what do we get? We get that pk plus 1 is equal to k plus 1 into k plus 2 into k, okay, plus 3 times this, okay, and 3 into k plus 1 into k plus 2. Okay, in this way, this first term is what now? It is pk. Okay, so k into k plus 1 into k plus 2 is simply pk. Okay, we can erase k from here and write it at the beginning. So you'll get k into k plus 1 into k plus 2, which is pk. So this will be equal to pk plus 3 into k plus 1 into k plus 2. Okay, now we know that pk is divisible by 6. We have to prove, why do you know it is divisible by 6? From this assumption. We have to prove that 3 into k plus 1 into k plus 2 is also divisible by 6. How can we prove this? K plus 1 and k plus 2, we can notice that they are two consecutive integers. Okay, they are two consecutive integers. It means one of them is odd and the other has to be even. Okay, so an even times an odd. Okay, an even is what is divisible by 2. Okay, so an even number is denoted usually by 2m, for example, and an odd number is denoted by, for example, 2m plus 1 or 2n plus 1 or whatever. Okay, in this form, this is an even number. This form is an odd number. Okay, so if one of these is even and the other is odd, then one of them is divisible by 2. Okay, the even number is divisible by 2. So we can write this whole part, 3 into k plus 1 into k plus 2, as such. This is equal to pk plus 3 into an even number times an odd number is always an even number. Okay, for example, 4 times 3, it's 12. 6 is an even number times whatever, for example, times 5, it's 30. Okay, so because one of the even number, one of them is even, and one of them is divisible by 2, so the product is divisible by 2. So this can be written as 2 times some natural number. We can call it L, M, whatever you want. Okay, now 3 times 2 is what? 6, of course. So pk plus 6L. Now since pk is divisible by L, pk is divisible by 6 and 6L is divisible by 6, then pk plus 1 is divisible by 6. Okay, so pk plus 1 is divisible by 6. The reason that pk and 6L are divisible by 6. Okay, 6L because it's 6 times an integer, pk because pk from the assumption is divisible by 6. Okay, this is the main step of the induction, and then E is explain or conclude. Okay, so in this step we simply write, okay, thus or hence or therefore, thus Pn, which is equal to n into n plus 1 to n plus 2, is divisible by 6 for any natural number n. Okay, for any n belong to this set n, it means the set of all natural numbers. Okay, after learning about the induction, we started learning about the sequence. We defined a sequence as an ordered list of elements that usually follows a specific pattern. Okay, like the set of the sequence of even numbers or odd numbers. Another way to define a sequence is a numerical sequence is a real function whose domain of definition is the set of consecutive natural numbers. Okay, and it takes as an input only natural numbers. As an output, it can give us anything. And we learned 3 ways to express a sequence. Okay, the first method is listing. For example, we can list the set un. Okay, when we write un like this, it is the nth term of the sequence. When we write un in parentheses, this is the sequence, the name of the sequence un. Okay, so we can name un as 0, 2, 4, and so on. So 0, 2, 4, like 6, 8, and this is the set of what? Of even numbers. Okay. We have to write in listing definition, we have to write at least 3 terms, okay, to know what the sequence is. Another sequence here, for example, is Vn, okay, 1, 2. Why we have to write 3 terms? Because if you write only, for example, 1, 2, it's not enough. We can continue 1, 2, like 3, 4, 5, all the natural numbers, or we can continue as 1, 2, 4, 8, and so on. Okay, 4 is enough. If we write 1, 2, 4, it means we have to continue as 8, 16, 32. Okay, multiply always by 2. And we took also a sequence that is the Fibonacci sequence. Okay, Fibonacci sequence needs also more than 3 terms to start with. So we have 1, 1, 2. Okay, and we add the 2 previous terms in order to get this term. So we get 3, 5, 8, and so on. Okay, so 2 plus 3 gives us 5, 3 plus 5 gives us 8. This sequence is called the Fibonacci sequence. Okay, Fibonacci sequence. And this sequence is what? 1, 2, 4. If we said it is the multiples of 2, is this correct or not? For example, 6. Will 6 be in the list? No, because we have 1, 2, 4, 8, 16. Okay, so because 6 is not in the list, then these are not the multiples of 2. These are the powers of 2. Okay, why? Because 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 cubed is 8, 2 to the power 4 is 16. Okay, so we are just multiplying by 2. Another way of expressing a sequence is in explicit definition. Okay, so for example, if you have to write un in explicit definition, we write it as un is equal to 0 to 4. We can write it simply as 2 times n. Okay, if n is 0, then 2 times 0 will give us 0. If n is 1, 2 times 1 will give us 2. 2 times 2 will give us 4. Okay, and we say that 0 is the first term of the sequence, 2 is the second term, 4 is the third term, and so on. Okay, Vn, now Vn is the powers of 2, so we can write simply 2 to the power n. Okay, and when n is 0, 2 to the power 0 is 1, 2 to the power 1 is 2, to the power 2 is 4, and 2 to the power 3, the next number here will be 8, and so on. Okay, Tn cannot be exactly denoted in explicit definition. Okay, so not all sequences can be written in explicit definition. In implicit definition or recursion, it is writing a sequence in terms of the previous terms. For example, un, the set of even numbers, okay, can be denoted as such. Okay, we say that the first term, let's take u0, is equal to 0. And to find the term, for example, un plus 1, you simply find the previous term un and add 2 to it. Sorry, u0 was 0 in the first. Here, u0 is 0 in the set of even numbers. Okay, 0, 2, 4. So the first term is 0, and the second term is u0 plus 2, which is 2. The term after it will be 2 plus 2, which is 4. Okay, and so on. And now Vn, to find Vn, we denoted as the first term was 1, okay, because 2 to the power 0 is 1. Now to find also any term, for example, to find the n plus 1 term, we have to find the term before that, so the term Vn, and multiply it by 2. The first term is 1, times 2 will give us 2, times 2 will give us 4, times 2 will give us 8, and then 16, 32, and so on. Okay, it's not always necessary to write n plus 1 in terms of n. Okay, we can write, for example, Vn in terms of Vn minus 1. You need to find the term Vn. Just simply find the term Vn minus 1, you need the term previous to Vn, and multiply it by 2. Now, the Fibonacci sequence can be denoted or can be expressed or written in implicit definition or recursion, but we have to define two initial values. So T0 is equal to 1, T1 is also equal to 1, meaning the first two terms are 1 and 1. And now to find any term, the term Tn plus 1, okay, or we can write it as only Tn, we said. So Tn is simply the term previous to it, Tn minus 1, plus the term previous to that, meaning the sum of the two previous terms. Okay. We also learned about specific numerical, special numerical sequences, okay, that are arithmetic and geometric sequences. Arithmetic sequences are sequences when we are adding a constant term. Okay, let's take an example. For example, the arithmetic sequence. Okay, we have, for example, let's say 2, and we are adding always 3, so 3, 6, 9, 12, and so on. Okay, so we have a first term, let's say u0. The first term is u0, it's equal to 2, and we have a common difference d, which is how much are we adding. Okay, sorry, there's a mistake here. We can start by 0, for example. 0 plus 3, 6 plus 3, 6 plus 3, 9 plus 3, 12, and so on. So the first term here is 0, and the common difference is 3. Okay, so we have started at 0 and we are adding 3. This is different to the geometric sequence, which is, for example, let's start at 2, okay, and multiply it by 3, let's say. So 2 times 3 is 6, 6 times 3 is 18, and so on. Okay, 18 times 3, for example, it's 30 and 24, so it's 54, and so on. So here the first term, let's name the sequence Vn. The first term, we can call it V0 and we can call it V1, we said. Okay, so this is V1, for example, is 2, and the common ratio here, okay, the common ratio is the number that we are multiplying by, it is 3. Okay, we are multiplying by 3 to move on from any term to the term after. Okay, so this is the general definition of a geometric, of an arithmetic sequence. It is un plus 1 is equal to the previous term un plus d, and we found a relation between two terms, any two terms in the arithmetic sequence and any two terms in the geometric sequence. We wrote both types of sequences in explicit and in explicit expression. Okay, so u0 plus nd is the arithmetic sequence. u0 times r to the power n is the geometric sequence. Why is this correct? For example, if you want the fifth term in the geometric sequence, okay, you just start at u0, you multiply by r, so u0 times r will get you to u1. u1 times r will get you to u2. So شو صار عندنا؟ صار عندنا u0 times r times r squared times r again we'll get to u3 times r again we'll get to u4 times r again we'll get to u5. Okay, and we also took a property and we derived this, how to find the sum of the first n terms. Okay, we derived this in class. We got these two summations. We proved why they are correct. This gives us the sum of the first n terms. So we can start here at u0 or at u1. So u0 until un will give the sum of these first n plus 1 terms. Why are these n plus 1? We said because we started at 0 and we ended at n. So we have n plus 1 terms here. And the sequence Tn, or the series Tn, this series has n terms. So these are the sum of the first n plus 1 or n terms of the sequence. We also learned more about sequences. We have here applications on arithmetic and geometric sequences, how to find the relation between any two terms and the sum. And we talked about the sense of variation of a numerical sequence. If un plus 1 is greater than un, it is increasing. If it is less than un, it is decreasing. To know this, we simply find the difference, un plus 1 minus un. Here, an plus 1 minus an. If the answer is positive, then an plus 1 is greater than an, so it is increasing. If this answer is negative, then an plus 1 is less than an, so it is decreasing. Okay. Here we also talked about expressing this sequence as a function f of x. Okay. This function here, we can simply find its derivative. Its derivative is positive. Of course, then this function is increasing. If this representative function of the sequence is increasing, then the sequence itself is increasing. Okay, but this sometimes to find the sign of the derivative, it's hard. Okay, so we have to know both methods in an plus 1 minus an and the derivative of f. And finally, we talked about the boundedness of the sequence. Okay, a sequence can be bounded above or below. For example, we took the sequence un equal 1 over n. Okay, if you remember, the first term u1, we cannot start at u0 because 1 over 0 is undefined. Okay, u1 is 1, u2 is 1 over 2, which is 0.5, u3 is 1 over 3, so it is 0.333, u4 is 0.25 because 1 over 4 is a quarter, and so on. So we will stay decreasing until we are very close to 0. Okay, cannot reach 0 exactly, but we will be just above 0. So as you notice that all the terms are between 0 and 1. Okay, so we can say that un is between 0 and 1. Here we said that we can write the equal sign at 0, or we can take it out. In both ways, that's fine. Here 1 is called an upper bound of the sequence, and 0 is called a lower bound of the sequence. A lower bound, it means un cannot be less than 0. 1 is an upper bound, it means that un cannot be greater than 1. Okay. Also, they told us here that any real number, for example, greater than a or greater than 1 here is also an upper bound. Can we say that here un, the sequence un, has 3 as an upper bound? Yes. Why? Because un cannot be greater than 3. Okay, and we can write, for example, here that un is between -2 and 5. This will still be correct. Okay, so 5 is an upper bound of un because un cannot be greater than 5, and -2 is also a lower bound for un because un cannot be less than -2. It cannot be less than 0, so it cannot be less than -2. It cannot be greater than 1, so it cannot be greater than 5 as well. Okay, so we also tried these examples, and we tried finally to prove this sequence that's written in implicit form. By induction, we proved that it is greater than or equal to 2. Okay, we did it in a little bit different way. This was here a quadratic equation, so we found the roots. They were 1 minus radical 5 over 2 and 1 plus radical 5 over 2. Okay, we solved this in class, and we proved why this sequence is always bounded below by 2. Okay, it's greater always than 2. Okay, this is all for today. We still have one section in the limit and the sequence, which is the limit of a sequence. How to find the limit of a sequence, what happens when n goes to plus infinity. And after this, we will start by the exercises in this chapter. Okay. يعطيكم العافية and see you soon.